So hi everybody, I want to talk to you about the idea of at least in a probability. And in your textbook it's going to talk about at least once. And just so you know, this is Counting and Probability Lecture 18. And I hope this is the last video we have to make, but we shall see. Anyway, probability of at least once. So what does at least once mean? Because I want you to think about this in terms of what it actually means. So suppose we have the numbers in a set that are 1, 2, 3, 4, 5, 6, and 7. And that's a set that I have. And suppose I say, give me all the numbers that are at least 1. So at least 1 means greater than or equal to 1. So we want to list all the numbers, call them x, that are greater than or equal to 1. So think about what at least means. If I had said at least 5, that means it has to be 5 or greater. At least 20 means 20 or greater. So when I say at least 1, that means it has to be greater than or equal to 1. So in the context of probability and counting, we're always talking about the idea of at least in combinations with how many are there. All right? And so if I want to find the probability of at least one item, that would be one or more items in this group, which means, because I can see this set, I can see that that would be all 7 items. Okay? If I want to do it in terms of probability and say what percentage or what probability of these items are at least 1, that would mean that it's either all of them, or I can use the idea of complements, or not, if you wish. Since we know that the probability of an event is equal to 1 minus the complement of the event, the not event, then that means that if our event is the probability of at least 1 greater than or equal to 1, then that's going to equal 1 minus not at least 1. Well, what is that? Not at least 1, not greater than or equal to 1, is less than 1, or if you wish, less than or equal to 0. And that leads us then to the formula in the textbook, which on your textbook is approximately on page 656. So you can look that up on that page. But the formula is the probability of an event happening at least once is 1 minus the probability that the event does not happen. Or in other words, it happens 0 times. Okay? And you could take this, if I said at least 5, then it's 1 minus the probability that greater than or equal to 5 doesn't happen, which means it has to be less than 5, or if you wish, less than or equal to 4. So this is the formula that we want to use. So suppose I have a bag of marbles, and inside that bag I have 4 red marbles and 3 green marbles. And what I want to do is I want to perform a test where I draw out 2 marbles. So I want to draw, I want to draw 2 marbles without replacement. And what I mean by that is I'm not going to put the marble back in the bag. And by not putting the marble back in the bag, I create those dependent probabilities we were talking about yesterday, where the probability of something happening after something has already happened, so it changed the probability. And as we talked about before, one of the best ways to do these problems is to make a tree diagram. So what's going to happen? Well, we're going to first either draw a red marble or we're going to draw a green marble. And then on the second draw, if we drew a red marble, then we're going to draw either another red marble or a green marble. But if on the first draw we drew a green marble, then we're going to end up drawing either a red or a green marble as well. And so when we draw marbles, this becomes a diagram of that experiment. So based on the number of marbles in the bag, I want you to fill out this probability tree for me, and then we'll answer some questions about it. So take a look at your probability tree. Did you get what I got? So on the first draw there are 7 marbles, so you have a 4/7 probability of a red or a 3/7 probability of a green. And then now that you only have 6 marbles left, there are the probabilities in each of the situations given that you drew a red or a green first. So what we're going to do is we're going to do a dependent event again, which would be, let's say, what's the probability of drawing 2 red marbles? Or another way to say that is probability of drawing a red on the first one and a red on the second one. Or we could say, what's the probability of drawing a green on the first one and a red on the second one? So these are very specific probabilities, and we can do those quite easily. And from what we learned last time, we know that this will be the probability of a red on the first draw times the probability of a red on the second draw. So this problem becomes 4/7 times 3/6, which is equal to 12/42, which you could then reduce and write as a decimal if you wish. And a green and then a red, well, that will be the probability of a green times the probability of a red on the second draw, green on the first, and that will equal then 3/7 times 4/6, which is also 12/42. And you could reduce that to 2/7, or you could change it to a decimal. Both would be correct. So I've now written a new problem in light blue. And the way I would read this is, what's the probability of a green given, that's what the bar means, given that I got a red first? Okay? What's the probability of a green given that I got a red first? So what do you think that restricts me to in my tree diagram? Which part of it? That's exactly right. Given that I got a red first, it's going to restrict me to that part of the tree diagram. And what I really want is just the probability of the green. But I want it, the probability of a green, given that I got a red first. So the red first is right here, but then the green I'm concerned about is that one right there, given that I got a red first. So what's that probability? It's 3/6, or 1/2. And that is called a conditional probability. Conditional. Sorry, ran out of room. These were called dependent because it was an and probability. And this is called a conditional. And usually the word given is the word you're going to see most of all. Okay, let's pause this just for a second and go to the next slide. Now I just draw another diagram, but just so you know, it doesn't really matter how many marbles I have in the bag or what colors. When I look at a problem like this, I can set up a tree diagram really quite easily. In this case, I have 3 different colors. I have a green, a red, and a white. And then in each case, I could get a green, a red, or a white, or I at least need to talk about that. And I could fill out the probabilities much like I did before. And so what's the probability of X given that you get Y, and you could ask about that. So I could have what's the probability of a red given that I got a white first. So what's that going to restrict me to on this tree diagram? So I want the probability of reds on the second draw. So I'm looking there, but the only one I pay attention to is where I'm given a white on the first draw. And that's how you can narrow yourself down in a tree diagram. Now, tree diagrams can become unwieldy and get too big, so you have to be careful with that. The other thing is when you're given a conditional probability, that probability will just be the probability of getting that red right here. Whatever that probability is there, that will be the correct probability. Because it's just given this, we're just looking for a particular red. Remember that the dependent, the AND probabilities, will always be the lower branch times whatever upper branch probability I had. If you keep those things in mind, you should be able to get those problems correct. So what I have here is a contingency table, just recording, how many students are in each class, freshmen, sophomores, juniors, and seniors, and then whether they're male or female in the class. And we've seen these contingency tables before, because we know that we have to find these totals that I have listed down there in the white. Now, what we're going to do is conditional probabilities with a contingency table. So here are 2 typical problems, and if you had done the contingency table problems before and watched that video, then this should be very familiar. Before, what we said is, what's the probability that someone is a male and a junior out of the total number of students? Alright. I'm sorry, I had just a bit of a mistake there on my diagram. I changed a couple, this one and this one. I just noticed that. So I changed those 2 numbers and now they're correct. Anyway, as I was saying before, what we did is like, what's the probability of a male junior? And so what we would do is we'd say, oh, male juniors, there are 3 of them, and the total for male juniors is, or for all the students, is 212. So we would take the 3 and divide by the 212, and that would be the probability. And that's how you would do an AND probability on a contingency table. But now, what if I ask you the question, what's the probability that a student is a male given that he's a sophomore? Or a student is a senior given that they're female? So once you think about that and which parts of the contingency table you would use, write an answer down and then turn the video back on and check it. So to do the first problem, I want the probability of a male given that he's a sophomore. So here's all my males. I got 28, 62, 3, and 9 males in different classes. And the one I choose is the males given that he's a sophomore. So the area I am looking at are these 2 windows, males given that they are sophomores. Alright? I know this is correct because these are male sophomores, and I know that this is correct because this is the given that it's a sophomore. So what's that probability? It's 62 out of 125. Alright? And then the next one, what's the probability that it's a senior given that it's a female? A senior given that it's a female. Well, I need to look at all the seniors. And here are my senior females right here. And it's given that it's a female. So in this case, I want to take the row total right there. So I want the female seniors, or the probability of a senior, given that it's a female. So I start out with all the females, and then I want to find the number of senior females, basically. And so that probability is 13 out of 110. Now what your book will do is it'll give you a fancy formula for this. And if you look in your book on page 660, for instance, on this senior female, the answer will be the number of seniors intersect females over the number of females. Now, that's a good formula to memorize, but wasn't it just much easier to look at the table? Because senior females, and given that it's the total of females. And so it's much easier to get these problems looking at a contingency table or a tree. So that's all I have for you. I'll assign the rest of these problems for this unit tomorrow in class, and then you will have all you need to finish this chapter, or at least what we're going to do, and then we'll do a review assignment on Thursday. I'll probably give you the review assignment in class as well. Okay, talk to you later.